37 and 0 is going to make 37. 19 is going to equal 1, positive 1, plus 18. So 37 and 0, 37 is going to equal 0 and 37. 19 will equal 1 and 18. That's how we're able to find out what the other part of a reaction is. Electron capture. Anytime we hear the word capture, we know that it's going to happen before the arrow because it's actually part of the reaction itself. So since it's an electron capture, a proton is going to capture an electron, and when a proton and an electron are connected to each other, we know we get a neutron. So our proton number should go down, allowing our neutron number to go up, but our mass will stay the same. So 22 and 11 Na, sodium, captures an electron, so these two are going to kind of come together, and we're going to lose the proton in the process because the proton is going to become a neutron when it captures that electron. So we end up with 2210 Ne. Again, 22 and 0 make 22, 11 and negative 1 make 10. So the proton captured the electron, forming a neutron. Going back to our original concept that a proton and an electron smash together, make a neutron. Okay, our last type that we're going to talk about is something called transmutation. And transmutation is when some atoms combine, oftentimes in the form of helium, but they're going to actually send out neutrons. The atom's going to become unstable because it becomes too heavy, and so some neutrons get kicked out in the process. So in this example, we're going to look at aluminum, and we're going to basically smash together aluminum and helium. Now when I say smash together, I don't mean that they bond and that just the outside electrons are interacting. I mean that we hit them together with such force that the actual nuclei of the two atoms fuses. So we end up with a brand new atom. So in the process though, some neutrons can get kicked out because it just becomes unstable. So if I take 27 and 4 as my mass, I would end up with 31, which gives me 30 and the 1 neutron that gets kicked out. And then 13 and 2 gives me 15. And then again, remember, neutrons don't have a proton number because they're just a neutron. So 30 and 1 gives me 31. 15 and 0 gives me the 15. Okay, so let's say that we get to our end of course exam and we cannot remember beta, alpha, positron, any of that. Well, we can look at our Regents Review packet. So if you look at your reference table for the Regents Review and you turn to page 7, you'll see Table O, which is symbols used in nuclear chemistry. And it just kind of reminds us an alpha particle is 4 and 2 helium, a beta particle is 0, negative 1 E. Gamma, we don't really worry about gamma radiation. We have our neutron, our proton, and our positron, and just kind of reminds us of what these different notations will look like, and that's going to matter when we start looking at our reaction types. Okay, so let's just take a second and let's review our questions. So we had a handful of questions that we were responsible for being able to answer. We had to be able to answer how are nuclear reactions different from chemical reactions, and we know that chemical involves the sharing of electrons, the atoms and the mass are the same on both sides. Nuclear reactions involve the nucleus of the atom, and so although we end up with different atoms on each side, the mass is going to remain the same. What are the types of nuclear reactions? Well, we talked about 5 different types. Remember, emission means it's going to come on the product side of the arrow. Capture means it's going to come on the reactant side of the arrow. So emission will always be on the right side of the arrow. A capture will always happen on the left side of the arrow. And then how do nuclear reactions support the law of conservation of mass? We know that the numbers on top have to be equal on each side of the arrow, and the numbers on the bottom have to also be equal on both sides of the arrow. And so that's a way that we can kind of fill in the blanks when we're looking at some examples. So now we're going to look at examples. These are the examples that were provided for you on the notes. And I already have the answers written down. We're going to go through and look through the examples and talk about not only the example type, but also the type of reaction. Okay, so in order to do this, we're going to need our periodic table because we're going to have to be looking at proton numbers in order to identify elements. Okay, so I have this reaction. The first thing that I'm going to do is I'm going to say, okay, well, what type of reaction is it? I can see that an electron was kicked out of the reaction. And since an electron was kicked out of the reaction, I know that it's got to be a beta or an electron emission because an electron was emitted or sent out. So I can go ahead and identify the reaction type. It's going to be a beta emission or an electron emission. And I need to be able to just fill in the number that goes here. Okay, so I think about this as an equal sign. 3 equals what plus 0? Well, that's going to be a 3. 1 equals what plus negative 1? Well, the only thing that would fit there would be a 2. 2 plus negative 1 is going to equal 1. So I have to look at number 2 on the periodic table. Number 2 on the periodic table is helium. So helium would go there. And that's basically all I have to do is I use the arrow as an equal sign. I make sure the numbers on the top and the numbers on the bottom are equal, and then I can identify the reaction based on what kind of particle left. So let's look at my next example. I have 232 and 92 uranium, and it's going to break down into 22890Th plus something else. So I need to figure out what would go here. Well, 232 is going to equal 228 plus some number. Well, what number would fit there? A 4. 4 plus 228 gives me 232. 92 equals 90 plus some number. Well, that's going to be a 2. So I have 4 and 2. Again, I look at the atomic number. Look on my periodic table. Number 2 is going to be helium. So I have to look back at my reaction types and I have to say, well, what type of reaction kicks out a helium atom? Well, I know that an alpha decay kicks out a helium atom. So I know that this is going to be alpha decay because the helium atom was kicked out. Okay, so keeping with our moving forward, again, just make sure that they're equal on both sides of the arrow. So 144 equals 144 plus 0. 58 equals 59 plus what? So what plus 59 is going to take me to 58? Well, a negative 1. So the only particle I know of that is 0 and negative 1 is an electron. So this is going to be beta emission because an electron was sent out of my reaction. Okay, so let's look at number 4. Number 4 is 65 and 30 zinc, and I got to fill in my blank. First of all, I know that this is a positron emission because it happened on the product side of the reaction. And I know that I can see that it's a positron. So 65 is going to be 65 and 0, and 30 is going to be something plus 1. So that would have to be 29 plus 1. So 29 plus 1 is going to be, let's find who number 29 on my periodic table is. Number 29 is copper. So I'm going to fill in copper, Cu. Okay, closing in. 209 and 84 plus something. Well, I know that this is going to have to be some sort of capture reaction because my particle is being added to the reactant side. So I'm going to figure out what type of capture reaction it is by using my numbers. So 209 equals something, 209 plus something equals 209. Well, the only thing that can be is a 0. 84 plus something is going to equal 83. Well, 84 going to 83 is going to have to be a negative 1. Well, I know that 0, negative 1 is an electron. So this must be an electron capture. Again, remembering that it's capture because it's happening on the reactant side of the reaction. Okay. 236, 92 uranium equals 141, 55 cesium plus something plus 3, 0, and 1 neutrons. Well, I know that neutrons are being emitted. So since neutrons are being emitted, this has to be transmutation. Okay, so I just need to fill in my blank. But I want us to notice, see how it has a 3? That means I have to distribute it to both numbers. So 3 times 1 is really going to make this a 3. 3 times 0 is going to keep it a 0. I just need to keep that in mind. Okay, so 236 is going to equal 141 plus something plus 3 ones. So 141 and 3 gives me 144. So I have to say, so I have 144 plus what to give me 236? So if I need to type into my calculator, I can. So I knew I had 236, but I'm going to subtract 141, and then I'm going to subtract 3. And when I do that, I get 92. So let's look at my numbers on the bottom. I have 92, and then I have 55 plus something plus 0. Even though there's 3 zeros is still 0. So I can say 92 minus 55 minus 0, and I'm going to get 37. So again, I look at my bottom number to tell me who that has to be. So I look back on my periodic table. Number 37 is Rb, rubidium. So Rb. And again, I knew it was transmutation because I had neutrons being kicked out. Okay, so those are some of my nuclear reaction equations. Again, remember, all I did was make sure that the mass on the top and the mass on the bottom were equal to each other. The numbers on the top and the atomic number on the bottom was equal to each other, and I was able to identify by using either my notes or my Regents tables. Okay, so a couple more example problems that I want to do. I have 3 more that I want to do, and the 3 reactions I have to do with writing the entire reaction. Okay, so here's my example. Xenon 131 undergoes electron capture. What would that look like? Okay, so I know that I have Xe 131 because this is going to tell me the mass. So I have to look at who Xe is on the periodic table. Xe has atomic number 54. So I have 54 here on the bottom. And it's going to be capture. Well, anytime it's capture, it happens on the reactant side, and it's electron capture. Well, what's an electron? Electron is 0, -1 e. And let's see what we make out of that. Well, 131 and 0 is going to make 131. 54 and -1 is going to make 53. Who's 53 on the periodic table? I, or iodine. So I knew that I could fill in this spot because it was a capture, so it had to happen on the reactant side of the arrow, and again, I just made sure that my numbers matched. Okay, so let's look at YB173 undergoing alpha emission. So I have YB, 173 is my mass, because they've given it to me, because the isotopes do matter in this. This is the type of reaction where the mass actually matters. YB is number 70. It's going to have atomic number 70. And I know it's going to undergo alpha emission, so that means it's going to kick out an alpha particle. So it has to happen on the product side. And I know that an alpha particle is 4,2 helium. So I got to figure out, well, what else is going to be left? So if I have 173, I have to figure out, well, what plus 4 equals 173? So it's going to be 169, and then 70 equals 2 plus what? 68. So 2 and 68 gives me 70, 169 and 4 gives me 173. So who is number 68 on the periodic table? Number 68 on the periodic table is ER, erbium. Okay, my numbers on the top equal, my numbers on the bottom are equal. It's emission, so we knew that this particle had to be kicked out on the product side. All right, BA138 undergoes beta emission. Emission, so again, I know it's going to have to happen on the other side of my yield arrow. So BA138, let's find barium on our periodic table. It's number 56, so its atomic number is going to be 56. I know that it's emission, so it's got to happen on the other side of my arrow, a beta particle. So I can't remember what's a beta particle. So let me look back at my reference table, and I can see a beta particle is really just an electron, 0, -1 e. So I say it's going to be kicked out, 0, -1 e. So what does that have to leave me with? Well, 138 on top, because 138 and 0 gives me 138. So 56 is going to equal something plus -1. So 57 plus -1 would give me 56. So let me find out who number 57 is on my periodic table. Number 57 on my periodic table is LA. It was emission, so it had to come on the product side of the arrow, and I was able to look up what a beta particle was on my Regents packet, and I was able to see that it was this. So that's how we would write reactions if they gave us the equation. They'll always give us our starting element, and then they will tell us what happens to it. Remember, capture is going to happen on the reactant side of the arrow. Emission will always happen on the product side of our arrow. Okay, so that's writing reactions. So you should be able to tell me how nuclear reactions are different from chemical reactions. You should be able to talk about the different types of chemical reactions, or I'm sorry, the different types of nuclear reactions. We can look at our Regents table for that if we need to. And then we know that how do nuclear reactions support the law of conservation of mass? The numbers on the top must be equal on both sides of the arrow, and the numbers on the bottom must also be equal on both sides of the arrow. All right, you should be able to balance your nuclear reactions now.